Good day everyone. In this video I'm gonna be showing you how to code UART, Universal Asynchronous Receiver Transmitter, in PIC18 microcontroller in assembly language. And I'm gonna be using the datasheet entirely. All the information I'm going to be using to code it is going to be entirely from the datasheet, directly from it, as in actual instructions from the datasheet with very little modifications. Okay, so let's begin. So first off, I'm gonna write the code for I'm gonna explain the code for asynchronous transmission. So the first thing to do to set up your UART is just want to change the view. Yes. So the first thing is to initialize the oscillator, and to do this you have to go to the first thing is to have a title and then a list, and then you have to include this file. It's P18 F45K22.inc. It basically lets you use names such as OSCON, IRCF2, etc. You won't be able to, the compiler won't understand these unless you include this .inc file. And next you have to do your configuration bits setup. If you already know this, you can just skip this section. So the configuration bit setup is basically FOSC int IO67, which basically means the setting is for the internal oscillator block. And the next setting to do is to ensure that the watchdog timer is off. And the next one is to ensure that MCLRE is external MCLRE, not internal, not EXT MCLR. Choose that option. And LVP should be on, low voltage programming. And I think that's it. That's the config bit setup, and you generate source code to output. You copy it and you paste up there, and that's that. And the next you have to type this. This essentially is how you tell your where the code starts from, basically. So it's org00h and go to init, and this is for the interrupt for the ISR. org08h go to ISR. Once again, if you know all these, you can just skip this section of the video and go to it. And to initialize, we have to call the oscillator. We have to initialize the oscillator. And in this case, it's been initialized to 4 megahertz. Let me show you that in the data sheet. Just change the view again. So in the data sheet, you have to go to it's up here somewhere, oscillator module, and if you would notice there are two registers here, register 2.1 and register 2.2. So the one of concern is OSCON. And if you look here from bit 6 to bit 4, let me just zoom in on that. From bit 6 to bit 4 for 4 megahertz, which I use in this case, you have to set bit 6, clear bit 5, and set bit 4, and then you get 4 megahertz for the OS card register. That's what you have to do for that. And next, let's go back there, and that's how you set that up. And obviously for the other, if you want to set up say for instance you wanted 1 megahertz, say for instance you wanted 1 megahertz, and then you would set bit 5, set bit 4, and clear bit 6, etc., just like it says here. So I'm just gonna go back to the UART section. Yes. Okay. So next, so that's the first part of the code, and then the second for the initialization. This is for oh sorry, let me just change. Yeah. Okay, so that's the first part of the code, which is to initialize the oscillator, and the first part of the initialization, and the second part of the initialization is to initialize the UART, and that's what we're going to look at, and that's where we're going to be coding directly from the datasheet, from information directly from the datasheet. And go to the section of the code. Okay, just open that up. Now I'm just going to open the PDF. Okay, so when you open the datasheet, you want to search for the section that says asynchronous transmission setup. So here, so that's going to be on page 262 of the datasheet, and we're going to start from the first one. So first, initialize the SPBRGHX register pair. The X represents 1 and 2 because there are 2 UART modules in this particular PIC microcontroller, so that's why this it could be 1 or 2. So SPBRG1 or SPBRG2, etc. And so the first step says initialize this register, the SPBRGX register pair, and the BRGH and BRG16 bits to achieve the desired baud rate. So this basically means we have to input a number into SPBRG1, and we also have to initialize the BRGH and BRG16 bits to achieve the desired baud rate. And it tells us C section 16.1 UART baud rate generator. So I'm just going to click on that. As you can see here, there's a formula in example 16.1 on page 272 that basically tells us how to calculate the value for the SPBRG GHX SPBRGX register pair. It's most the SPBRGH is the most significant 8 bits, so the pair makes up 16 bits, but most of the time you're just gonna need the lower pair, which is just 8 bits, so you don't have to worry about the SPBRGH. Most of the time the SPBRG is usually enough. Usually in cases where you're gonna need both is if you're going for a really low baud rate at a high oscillator frequency, which is very unlikely, which is you're probably not gonna need that. Like for example, in this example, we're gonna be using 4 megahertz, so don't worry about the upper 8 bits. You only have to worry about the SPBRG in this case. So yeah, so this formula essentially, let me just zoom into that. Okay, so this formula essentially tells us how to calculate the value to input into the SPBRG register, and where those bits, the BRGH and the BRG16 bits, come in is in this table down here. So if you look at this table, these are the settings you have to use. So if the BRGH bit is cleared, if both bits are cleared, BRG16 and BRGH bits are cleared, then you have to use this formula to calculate the value for the SPBRG register. In this case, N represents the SPBRG value, but as you can see here, it's 64. We clear the BRG16 and BRGH bits, then we're going to have to use 64 in our formula, which is essentially this formula up here. But if we set the BRGH bit and clear the BRG16 bit, then we could use this formula with the 16. So that means we're going to replace this 64 here with a 16. And essentially what that does is it gives us a higher value for this, because the higher value for the SPBRG register, because sometimes you might want a high baud rate at the low oscillator frequency, relatively low oscillator frequency, and in that scenario this value might be about what is it, maybe 5 for instance. It might be really low. You might want to have a higher value there, you know, I guess for stability or something, and you might want a higher value there. So to get a higher value, the 64 has to go down, this value has to be reduced to 64. So if you go to 16, so if you could go down to 16, and this value of 25 could be higher. So that is in essence a way to understand the reason why we might want to change BRGH from 0 to 1. And that's, so in this example we're going for a baud rate of 19,200, and the oscillator speed, the frequency of the oscillator is 4 megahertz. You could do that on your calculator. So FOSC is going to be 4 megahertz, desired baud rate 19,200, and we're gonna set the BRGH bit, which means 64 here is not going to be 64, it's going to be 16, and you find that the value we get from that is 12. And that's exactly what's we've done in code. Open that up. We look up there. So we moved 12 into the SPBRG1 register, and you look down here. As you can see, we've set the BRGH bit and we've cleared the BRG16 bit. And in cases where the datasheet, for instance, like in cases like this, where, let me just go to page 262. In cases where they just give you bits like that and you don't know what registers in, I suggest you just open up the ink file. So there's a, so if you remember in the code, go up to the top there, you remember this file, so you have to search that file. I'm gonna put the link to it in a zipped file, a link to this file. It's gonna be in a zipped folder, including all the other PIC18 ink files. So if you open up this ink file, you could actually find the register in which a bit is located. So what we're looking for now is the BRGH bit. So I'm just gonna show you how to find it in that. So this is a notepad document, and I'm just gonna go to, yes, so this is the ink file. So if you just search BRGH in the ink file and keep until you find the bits settings. So as you can see here, you can see BRGH is in the TXSTA1 register, and also you could, instead of writing, let me just zoom into that, instead of writing TXSTA1, you could also write TXSTA in this case. You don't have to include the 1, but if you're using the second UART module, you have to use TXSTA2 in that case. So here, as you can see, the BRGH bit is in the TXS2A1 register. So that's how you can find that. And for the BRG16, you just do that and search again, BRG16. And here, as you can see BRG16 is in the bold 1 con register, or the bold con register. You can use both. But for the second one, I think you have to say bold 2 con. Let me just check there. Oh, bold con 1. Yeah, you could also use bold con 1. So as you can see, the BRG16 bit is in the bold con 1 register. That's important to note. And the next step for coding it, for doing the UART setup, is so the next step is set RX and TX. Set RX and TX controls to 1. So once again, this RX and TX are bits. So once again, you could open up the inc file and just check. Remember, we have to set them according to the datasheet. So you just go RX1. You see RX1 there. So you see RX1 is a bit, so you have to go up, find it. As you can see, it's in port C register. It's actually in a TRISC. It's actually in a TRISC register. Because remember, this is it's direction control, so it's about direction control. So you have to use the TRISC register in this case, not port C. So let's just go back to the code. As you can see here, in the UART init. So you can see here it says set to the RX and TRISC, set the RX x / DTX and TXX / CKX TRISC controls to 1. It's supposed to be to 1. So that's that. And set the controls to 1, and that's done there. And then the next step is to enable a synchronous serial port by clearing the sync bit. So the next step is to enable a synchronous serial port by clearing the sync bit and setting the SBEN bit. And the next one is, if 9-bit transmission is desired, set the TX9 control bit. A set 9th data bit will indicate that the 8 least significant data bits are in the address when the receiver is set for address detection. So if 9-bit transmission is desired, so we don't desire 9 bits transmission, we're going to use 8-bit transmission in this case. So we'll clear that bit. I just want to go through the rest of them and then I'll show you the code afterwards. So, and 5, set the CKTXP control bit if inverted transmit data polarity is desired. So in this case, if you made a DIY UART bridge with PIC18 F14K50 microcontroller, then you would need to set this bit for inverted transmit data polarity. But if you buy one off the shelf, like a PL2303 for instance, UART to TTL converter, then you would not need to set this bit, you just clear it. And next is enable transmission by setting the TXEN control bit. This will cause the TX XIF interrupt bit to be set. Remember, anywhere you see X in my controller, it usually means 1, 2 or more numbers. It depends on how many modules the microcontroller has. So this will cause the TX1IF interrupt bit to be set in our case. So enable the transmission by setting the TXEN bit. So as you can see in initialization, you need to focus on basically when it says enable. To enable something, you have to set a certain bit. You have to focus on those. So, and the next one is if interrupts are desired, we will not be using TX transmit interrupts in this case, so you don't have to worry about that. So if 9-bit transmission is selected, the 9th bit should be loaded into. So we're not using 9-bit transmission, so we could ignore that for now. So load 8-bit data into the TX reg 1 register. This will start transmission. So we're not transmitting yet, so all we want to do is just initialize for now. So that's basically what datasheet said, and I'll show you the code which follows exactly these steps as microcontroller, as the datasheet suggests. So I'm just opening that up, lab expansion. And also, if the explanations are too long, you could just skip right on to the end, or just go ahead and download the code and have it go. And so this is where it was. So it says here, the sync bit must be clear for asynchronous communication, and that's what we did. The sync bit was cleared. And also, if you don't know where the sync bit is, you could use the same method I showed earlier, which is basically open the inc file, search for sync, and you would see the name of the register up top. So it will say TXSTA bits, and it will show sync as one of the bits of the register. And so it says the datasheet told us the sync bit must be clear for asynchronous operation, and that's what we've done. Remember, the sync is going to be set if we want synchronous communication, but in this case we're going with asynchronous. So as it says in asynchronous transmission setup. And the next step was enable the serial port by setting the SPN bit, and that's what we did. The SPN bit was set, and that's in the RCSTA register. And the next step basically, and it said, this is not the next step of the datasheet. It just continues as it does in the datasheet. So if 9-bit transmission is desired, set the TX9 control bit. So you said BCF TXSTA1 TX9. So we cleared the TX9 bit of the TXSTA1 register. And the next, if interrupts are desired, set the we're not looking at these yet. So that essentially is the transmission setup. These first 6 lines are the transmission setup. We're gonna look at the receive just now, but we're not looking at them yet. Oh yeah, sorry, apologies, we're not done with that yet. So the next one, set the CK TXP control bit if inverted transmit data polarity is desired. Like I said, if you made one a UART bridge, then you would need to set this bit of the board count 1 register. And also, like I said, if you're looking for this bit, you should go to the inc file, search it, and look at the name of the register up top. And for these, I'm ignoring these for now because that's for the receive. I'm not looking at the receive just yet. We're just looking at the transmit for now. And BSF, enable transmission by setting the TXEN control bit. And that's how enable transmission by setting the TXEN control bit. And that's exactly what was done here. The TXEN bit of the TXSTA1 register was set. And that was that, and that's that, and that's basically the transmission setup. And to actually do UART right, let me just go back to the datasheet and show you where it informs us how to do a UART right. Okay, so here, so you can see here in the last point, it said load 8-bit data into the TX-Reg1 register. This will start the transmission, and that essentially is what has happened here. And so first we'll load that, but then and like it says here, this will start the transmission. But the problem with that is when we want to send multiple bits, we have to have a way of knowing when we could send another another 8-bit set of data. So each time we send, usually we send a character, we're sending a character through the UART, and in this case we're using 8 bits. It's going to be 8-bit per character, loading an 8-bit data. So in this case we're gonna need a way to know when this 8-bit data has been sent to, so we know, and when we could send another 8-bit data. It's gonna make much more sense when I show you the code. My explanation for that is not so good. So here, this is how we know using the TSR state. So it says here, the TRMT bit of the TXSTA1 register indicates the status of the TSR register. So essentially, the TRMT bit is going to be set once the TSR register is empty, so which means it's ready to be written to again. So the way it works is once you write the TX-Reg register, transmission starts right away, but transmission occurs in finite time. So after it's done, the TX-Reg register automatically clears out. So when it clears out, we could write to it again, but when it clears out, basically the TRMT bit gets set. So basically we're gonna use the TRMT bit as a trigger to know when we could write another bit into the TX-Reg register, which in essence is writing an 8-bit data into the terminal. I'm gonna show an example just now, but before we do that, let me just go back to all of that. And so that is the essence, is what it does here. UART right. So move the data to TX-Reg1 to begin transmission, and so you move the data from the this section of code assumes that you've already moved the data you want to send into the working register. And then you move into the working register, and then you move what's in the working register to the TX-Reg1 register, and then afterwards you have to start polling the TRMT bit of the TXSTA1 register, and the TRMT bit is set. This is the information from the datasheet. The TRMT bit is set when the TSR register is empty, and is cleared when a character is transferred from the TSR register. When a character is transferred from the TSR register from the TX-Reg register. So in essence, what that section that I just read says is, once we write into the TX-Reg1, the TX-Reg1 automatically sends that to the TSR register. The TSR register is what makes us see whatever we just send on a terminal, for instance, sent from the microcontroller to a terminal, for instance. And so when that happens, the TRMT bit, it gets cleared, it becomes a 0. So when that becomes a 0, then we're gonna start polling here. So we're gonna go to the next line. So we're first gonna bit test the function, bit test trmt, skip the next line if set, but it won't be set. So we're gonna go to this line, and this line in essence means this dollar -2 sign in essence means go to the previous line. So that's what this line means, $-2. Let me just put a comment there. Branch to the, okay, all caps, branch to the previous line. Okay, so that's what that does, and it branches to the previous line. But once the TX-reg1 register becomes empty, the TRMT bit becomes set. So therefore we could skip this, and that means the data we just sent is on the terminal now, has been sent out. And that in essence is UART write. That's how we'll do a UART write. And now let's go to the read. So let's just go back to datasheet. Asynchronous. We'll just go to asynchronous receive setup. So in the asynchronous receive setup, just show you. So it says here initialize the register pair. We've already done that. Set these trace controls to 1. We've already done that. Enable serial port by setting the SPN bit. Already done that. The sync bit must be clear. Also already done that. And now this is what I wanted to show you. If the interrupts are desired, set the RCXIE interrupt enable bit and set the GIE and PIE bits of the incon. So sometimes in cases where we wanna interrupt the code flow when we receive an 8-bit data from the UART module, want to interrupt the code, then we would have to set up a receive interrupt. So an interrupt in essence is it cuts the flow code. So instead of polling constantly, which would take a long time, polling in essence is what we did. Let me show you what polling is quickly, so I don't lose you there. Okay, so this, just go back down there. Okay, so this in essence is polling right here. This section I highlighted, that's polling, because we're constantly testing a bit, right? We're constantly testing a bit, and if this bit never gets set, we're essentially never gonna get out of this loop. It's gonna stay in this loop for life, forever. It's just gonna stay there forever, right? But interrupt kind of solves that issue for us. So in interrupt, we don't have to stay polling like this. We don't have to stay in a loop. So so in essence, when a bit gets set, it's automatically just gonna jump to us and gonna run a section of code every time a bit gets set. So we don't have to stay here and pull the bit as such, bit test function, skip if set. We don't have to do that. It will just automatically set that bit and jump to a section of code and run that code. I'm gonna show you what I mean in a second. Okay, so let's go back to the Foxit PDF. Yep, right there. And so if interrupt desired, set the RC interrupt enable bit and set the GIE PIE bits of the incon register. So that's that. And if 9-bit reception is desired, set the RX9 bit. We don't desire that, so we'll just clear that bit. So set the DT RXB if inverted receive polarity is desired. It's not desired, so we're not gonna set that. So enable reception by setting the CREN bit. So we wanna receive data, so we'll set that bit. And the next basically explains how receive is gonna work. I don't want you guys to worry too much about 10. 11 for now. Just put that out there. Okay, so if you look at the 8, the RC1RF interrupt flag bit will be set when the character is transferred from the RSR to receive buffer. An interrupt will be generated if the RC1RE interrupt bit was also set. Okay, so in essence, what this says is once we've received 8-bit data from the UART, once there's a data in the RC1 register, this bit is gonna be set. That's what that means. So 9 says read the RCSTA register to get the error flags. Don't worry about that for now. It's not necessary. So 10, get the received 8 least significant bits from received buffer by reading the RC1 register. Okay, so let me just show you guys in the code. Yeah, let's go there. So this is the receive setup right here. So BSF, PIE1, RC1IE. Yeah. So if interrupts are desired, set the RCXIU interrupt enable bit. So we're using the UART module 1, so it's going to be 1. So once again, to find the register containing this bit, is go into the inc files and check that out. So you set RC1IE of the PIE1 register to enable interrupt, and afterwards you have to set to the GIE and PIE bit in con register according to the datasheet, and that's what was done here. And next, where is that? Yeah. Oh, this is what we're looking for. If 9-bit reception is desired, set the RX 9-bit. It's not desired, so BCF will clear that bit. So also set the DT-RXB if inverted receive polarity is desired. If you make a DIY UART bridge, which you could if you wanted to, there's a way to do that. I'm not going to show you how to because I've never done that before. If inverted receive polarity is desired, but you know it's not desired, it will not be desired in this example because if you bought off-the-shelf UART TTL converter chip or module, you wouldn't need to invert the polarity because I think it already does that for you in there, takes that into account. So you're just going to clear mat DT-RXB bit of the both con1 register. And lastly, enable reception by setting the CREN bit. Right, so yes, enable reception. Okay, so just let me show you one last thing over there in the datasheet, just so you know when to stop when to stop initializing your receive. Let me just go back there. Yes, datasheet. Go back. So here, as you can see here in 7, it says enable reception by setting the CREN bit. So as you can see here, the RCIF, it's right here, it's just telling you about the functionality of the interrupt flag bit and what happens when a character is transferred from the RSR to the receive buffer. Essentially, it's just telling you exactly how we're gonna receive. So that's not setting up anymore. That's just telling you how exactly we're gonna receive. So, and you see the next one, read the RCSTA register to get the error flags. And 10, it says get the received 8 least significant data bits from the receive buffer by reading the RC1 register. So as you can see, it's telling you exactly how to read, in this case, exactly how to receive the data you just read to get it, in essence. So that's not setting up anymore. So I'm just going to show you that now. And in this case, we're using an interrupt. Well, there are two ways you could receive. You could use one I call like a crude way, and the second is just I think the regular way, which is using an interrupt to receive. The more natural way of doing it is to use an interrupt to receive. And I'm just going to show you that one first, and then I'll show you the more crude way afterwards. Okay, let me just show you the code now. Just go to the code. Okay, there we go. So yes, no, that's not it. So remember what I said about the ISR? Instead of staying in one position and just polling forever, it automatically gets set. Bit automatically gets set, and you jump to run a section of code. Well, that section of code is the ISR, interrupt service routine. So this is that section of code over here, and to return from that section of code, you have to say RET FIE. Anyway, this is the section of code, and here, as you can see in this line here, well, this first two lines, well, I said no polling, but this line is important for cases where you have multiple interrupts. So the only interrupts that exist in the microcontroller is not only the receive interrupt, there's also the external interrupt, there's also time interrupt. You will need to differentiate from these. So to differentiate, you're gonna have to check bits. Essentially, you're gonna have to check if the bit that was set was the RC, the receive one, or the interrupt one, or the timer one. I'm not gonna go through those in this video. It's not gonna, that's not in the scope of this particular video. Okay, so as you can see here, basically what I'm doing is this. You actually don't have to include this top two lines in this example, but it's better for future use to include them. So essentially what this does is to test the RC1RF bit of the PIR1 register, and if it's not set, it's gonna keep polling there. Well, in this case, okay, so the RC1RF interrupt flag bit will be set when a character is transferred from the RSR to the receive buffer. So once it interrupts, this flag is already set essentially. So it shouldn't land normally on this line, because remember, once it enters into the interrupt, this guy is already set automatically, because it was actually RC1RF that triggered an interrupt in any case. Triggered us going into this interrupt service routine. Remember, the reason we're in this interrupt service routine is because we enabled the interrupt in the initialization of UART right here. This guy was enabled. That's why we're in an interrupt service routine. If that was not enabled, then we would not be in this routine. So this guy, in essence, is the reason why we're here. So it's definitely going to be set. So once it's set, we're going to skip this line, skip the next line. Once again, this line essentially means branch to the previous line. It's kind of I don't know, a waste of space, I guess, to constantly label everything. So this helps a lot if you're not really into that, putting like actual labels on the next line, on the previous line. Anyway, just a side note. So bit test function skip if set, it's gonna skip this middle line here, and gonna move what's in the RC1 register into the working register. That's what this line does. Move if RC1, comma 0. It's gonna move that to the working register. Once it moves that into the working register, it's gonna call the UART write. And if you remember correctly, the UART write function, just jump there, assumes that you've already sent what you want to write to the terminal, to whatever terminal of your choice, into the working register, which we have done by doing that, by moving if into the working register. Back up there. Okay, move if to working register, and then we'll call UART, right? So this is essentially an echo program. So I'm just going to run that and show you the code functionality. Okay. It should take this would take a minute to run, unfortunately. Okay, and that's that. So now let me just show you the functionality on the terminal, on the actual code functionality. And just open that and close that. I'm just gonna type here the UART interrupt code is working, and there it works. Now I'm just gonna go back to imply. So what I did was I cleared, so you go to the receive interrupt enable RC1RE bit, and you just, it was set before, yes, and you just clear it instead. Now you clear it, yeah. And you could go ahead and clear the global interrupt enable and the peripheral interrupt enable, these two that are highlighted right here, but it won't matter because you already cleared the receive interrupt. So let's just run that to show that the code no longer works, and then I'll show you the other way. Usually most people just use in most applications, I'm guessing you're probably just gonna stick to the interrupt way of doing things, but sometimes the other way comes in very handy, you know, in situations where you just wanna prompt a quick receive. You might not wanna always gonna go into the interrupt, especially if your entire code is in the interrupt and you really don't wanna mess with it. You just wanna do a quick receive. Then you might, the other method I'm about to show you is prove very useful. And yeah, just run the code, share the purchase screen. Yeah. After disabling the RC1RE bit of the PIE1 register, the UART receive function no longer works. So I'm just gonna play that right now. And wait. As you can see, if I type here, nothing works. I hope you can hear me trying to type on the keyboard. There's no echo, which means disabling the RC1RE bit of the PIE1 register is disabled to the interrupt, so it no longer interrupts the code when I type here. So now I'm gonna re-enable the UART receive functionality using the crude method, and yes, re-enabling the functionality. Alright, I showed you in the interrupt, and only now it's not in an interrupt. So you go here, you receive the RCXIF interrupt flag bit will be set when a character is transferred from the RSR to the receive buffer. Essentially what that means is when we receive something, it's usually in the RSR buffer, and then the RSR sends it to the RC-Reg1, and after that happens, we have to know that that has happened, so the RC1IF bit is set, and that's how we know. So in essence, we could just read the RC-Reg1 register directly, but it will be 0, right? But the only way we could know if there's actual information in there, if there's something that's actually just been written there, is by checking if the RC1IF bit is actually 1. So that's why we have to poll this bit. So essentially what the UART read function does is it polls that bit, the RC1IF bit, and once it sees it's been set, great, it means there's something in the RC range 1, great. Move whatever's in the RC range 1 register into the working register and do whatever you want with it afterwards. And in this case we're going to echo to the terminal again, but this time without an interrupt. There, so as you can see, it's going to call UART read and then call UART write. This is very useful, as I'm going to show you later on. Well, not in this video, but this comes very handy because it's just a quick way to receive something from to receive an 8-bit data from, for instance, a user on a terminal. It's a real quick way to do that, and yeah, in essence is what it is. So let me just run that quickly and show the output. This should take a minute again. No. Okay, so I'm gonna share the Proteus screen using the crude method for receiving. Okay, the UART code works without the interrupt. Okay, full stop. Yeah, so the crude method also works just strictly from the datasheet. Well, 95% from the datasheet, and some of it, very few was added. Honestly, most of it was directly from the datasheet by words. Actually, all these comments are lifted directly from the datasheet, so directly plagiarized from the datasheet, these comments. Just to show you guys that you can actually code UART directly from information in the datasheet. And then in essence is UART. And well, just a quick recap on what was shown. First, you could do it with an interrupt. What this code does is it echoes whatever you typed in back out to you. And you could do it with an interrupt or without an interrupt. Well, and with an interrupt you have to initialize, you have to set the RC1IE bit of the PIC18 register, and without it you just clear that bit. And so just a quick recap of the UART initialization. First, we set up the baud rate according to this formula, which is the datasheet. You can just go back to the section where I showed that to you. And the next, also this has to do with the baud rate, with the calculation. So in this case it's going to be 64. It's going to be 64 instead of 16 over there if BRGH was cleared, but in this case it was set, so it's 16 over there. And the next step is oh yeah guys, I forgot to tell you about this. Before you make any changes to the TRIC register, you have to disable analog functionality. You have to do that or nothing will work, or this will not be set. It will not turn into a digital. The pin won't operate as pins of port C won't operate as digital pins. They will stay analog or at the default state, which might be analog. So you must disable analog functionality by doing that, by having this move literal to bank 15, because console C is in bank 15, and you have to clear it, console C, Basically what that does, it disables analog functionality of port C. Oh, I think that's the part that's not explicit in the datasheet that I added. That's the little part there, and it's actually really important. And anyway, so yeah, so you have to set the RX1 and TX1 bit, and if you're confused as to where these bits are, just go back to the inc file. I'm gonna post that as well. I'm gonna put that in the link there. It's gonna be a zip file, so you have to look for the specific. You have to look for this particular inc file in there, which shouldn't be hard. It's just PIC18 F45K22. Look for that there, and you search. Let's just go back to where I was. Yes, that's where I was. And you search for RX1 TX1, you will find that the port, it says port C, but it's actually supposed to be tris C. Also, that's not explicitly stated in the datasheet. It's actually tris C. So you set those two, and next, according to the datasheet, the instructions, you have to clear the sync bit, which essentially means we're in a synchronous mode. You have to set the SBEN bit, which is serial port enable, clear the TX9 bit, which means we're not transmitting 9 bits, and this guy here, which is the MVP, in terms of using interrupts to receive. And also you have to, when you set this, it's not going to work if you don't enable global interrupt and peripheral interrupts as well. These two lines are needed, unless this line's not going to work out. And that's that. And inverted polarity, we don't need that, unless you make your own bridge from another microcontroller. Then you will have to set this bit in both common register, and the TXN bit as well. So you have to enable that to enable transmission. And the RX9, we're not receiving 9 bits, so it's cleared, and we're not inverted polarity. Well, just in case if you do that, then you would have to set this bit if you make one, and a continuous receive. And yes, you have to set that. That essentially is the initialization part. And before you do that, you could do this if you want. It's just a precaution. I think it will still work out fine if you don't do this, but just do it anyway for a precaution. Just clear all the registers, initialize them before initializing them in a way. And now for the UART read. Yes, is that you could use the ISR, which is this. And actually in the ISR, if all you're doing is just reading UART, you could just actually remove this part and move F directly from RCH1 into the working register and call UART right to echo that to the terminal for visibility. And this is the crude one, UART read, without using an interrupt. Without using an interrupt service routine. This is an interrupt flag over here. Receive interrupt flag, that's actually what it means. And then the UART write, which essentially you have to write to the TX-Reg1, then pull the TRMT bit of the TXS2A1 register to ensure that the TX-Reg1 is empty before writing to it again. And that essentially is UART. Apologies if that recap bored the living daylights out of you. I understand. So that's that. Apologies for the long video. Try to make it short next time. Anyway, good luck coding UART.